let's see. So what I mentioned last time was the, so let me recall first. Recall what I have a continuous time, not obtain xt with a transition matrix P sub T with so we have the okay, the P naught is supposed to be the identity matrix. I think I missed explaining that last time. It's an identity matrix, and it's just that. What do we have? So probability x t plus s is equal to a j, given that at time s and at the location I, x is I a, s naught is I naught. This is the same as probability I will be at j at this time, given x is equal to I, and this is dt. Jumping to j. Right. Okay, so that is a okay. This is the definition of a continuous time multiple chain. And okay, so the picture is something like this. To help explaining the what it is doing here is the following. So suppose start from the time 0. Remember, because now I have a continuous time, and so let's say I'm going to start a little x right here. All right. Again, because this is a continuous time, and so I'm going to stay here for some time. All right. I'm going to stay at s for some time. Let's say at this time, let's say this is time, say t1. Let's say. I guess I want to use the notation capital T1. Then starting from here, I'm going to jump. Let's say I'm going to jump to a location little y. All right. And then we're going to stay at y for some other time. So this is a time t2. And then from this, at this instant time, I'm going to jump to a location, let's say little z. All right. And then I will stay at z for another time, and then I keep jumping from there, basically. So that is the idea of the continuous time Markov chain. So remember, back in the day when you learned the discrete case, we don't have such a waiting time. In the discrete case, basically I'm going to jump like this, right? Pretty much like instantly and jump. So for each step, step 1, step 2, step 3, step 4, there is no so-called waiting time for the discrete. But here for the continuous time, because there is no like a first step or a second step, and so say starting from S, I will stay for some time up until the time t1, jump to y, and then stay at I will stay at y for another time. So remember the notation that I used to have. This is like a tau 1. This inter arrival time is tau 2, tau 3, and so on. All right. Okay, but I will come back to this in a moment. Here to help you understanding what does it mean, like the graph of a continuous time multiple chain. And so if you think about the Poisson process. So the Poisson process, all right. So let's see, what is it? This is time 0. This is the number of guests. 2, 3, all right. So from the time 0, I have no guest. I'm going to wait until the first arrival time. This is Poisson process, right? So until this time, when the first guest arriving, I'm going to jump. The number of guests now is jumped to 1. So I say this is answer 2. Okay? Yeah. This is the waiting time back in Poisson process. Remember, this is exponential with the rate being lambda. So then, when the first guest arriving, I'm going to wait my process. It's waiting for another time up until the time t2. The second guest arrived. And so, okay, so this time I'm going to jump to 2. And so on, jump to 3, keep going. This is time 3, right? And the fact is because they have what they have, independent increment. It has a stationary increment, and so you can check that the Poisson process will have to satisfy those two equations, namely the Markov property and the time homogeneity. Okay, explaining why it is a continuous time Markov chain. Of course, there is some math going on here. Where did I stop last time? Where did I stop last time? Where did I stop? Okay, so I confirm it has that transition matrix, right? And the okay. So what did I have? So from last time, what I did is I have, okay, so NT plus S B and J given and S B and I and S and N and S naught is I naught. Eventually I get down to the relation NT plus S minus NS is J minus I. And apparently this is equal to what recalling that is e to the minus lambda t J minus I and J minus I factorial. So I'll define this function here to be my transition matrix PT. Okay. And of course, this is only making sense if, as you can see, Poisson process only increasing up. It does not go down, obviously. And so J is supposed to be greater than I. So here, J is supposed to be greater than or equal to I. Of course, if J less than I, then it doesn't make any sense. It doesn't make any sense if J less than I. So I have to. And then of course, this, you do the same thing for the suppose a condition on no conditioning on the past, just on the SB and I, and we have the same relations. So similarly, let's say suppose I have this SB and J, conditional and SB and I. This is the same as probability T plus S minus NS being J minus I, condition of NS being I, and because this is independent of NS, so this is the same as minus NS minus I. So, okay, so I guess for the sake of completeness, E minus T, T, J minus I. Okay, so that is one particular example Note that renewal process in general is not a continuous time markup chain. So let me put a remark here just in case. So in general, a renewal process that we discussed back in the chapter 3 is this is not really a continuous time markup chain. All right. Not really. All right. It's only very specific for the post-sale process. Well, I guess I have another example, but let's just refer to the textbook. So for another example, see the lecture 1. So another example, namely, suppose I have a discrete time markup chain. So a discrete markup chain on a space S. All right. Independent. This discrete on space S is independent. The second is a Poisson process, and T a Poisson process. All right. Then we can check that the process x of t defined to be y evaluated as n sub t is a continuous time. And the way you check is pretty much similarly pretty much similarly. We try to get the transition matrix, and it has to satisfy the Markov property. But here, let me explain what is this doing here. To think about this, okay. Suppose I have let's say I have a starting time 0. All right. So this is my x of t. Sorry, this is t here. So xt is y x of t. All right. Okay. So what do I say? So suppose here I have two locations, x and y, and I have, let's say I have say nt is a number of guests. Let's say 5 guests. For instance, let's say up into time t, I have 5 arriving guests, and so the chance I'm going to jump from xt, all right, I'm going to jump from x to y here. So the probability, so x t is y5, all right, and so xt is equal to y conditioned on what do I say? So maybe a leap can happen, and t plus s, and that's equal to 2, for instance, all right. T plus s, x s is equal to y. This event here is the same as the event I have y sub 5, meaning y and y division on y2 is equal. Right? So the behavior of the xt is dictated from the nt and the y. Right? So sorry, this is t plus s. This is SE. Right. Let's go in here and I'm going there at that location. Okay. For instance. So how do we compute? So probability of xt plus s is equal to a spot x, and x of s is equal to a spot y. So what it is? All right. So let's compute transition matrix. Okay. So what is it here? So by definition, I need to have. I guess I want to go with this. Xt plus s in x and s in y. Of course, that's just a definition of condition of probability. That's in the middle one. Right? So now I'm going to use the fact that xt is defined through the y and the n. Xt plus s. Xt plus s is equal to y. Is that what I call? Oh, we'll call it x. Well, like this. I'm sorry, I should have. I gotta go back. So y x here. That's equal to y, given xs is equal to x, alright? The numerator, let me just check y and x, okay. So what is this? So this is the probability by definition y and t plus s is equal to y and s is equal to x. This is my definition of x. And then we're going to do the law of total probability. Whatever value I can take on the Microsoft process. So I guess I want to run from, well, what do we want to run from? N here, n starting from 0, and k starting from 0. Probability of y and t plus s being y. Y and s being s, and I have n t plus s minus ns being k, and s being n. Right? Whatever I can take. Okay, just law of probability here. Alright. So now that is the same. Remember, this is the same as nt plus s is m plus k, and s is equal to n. All right. So I can replace the variable index by the fixed integers. Still the same sum. I have y. What I have here, m plus k being y, n being x. Same. All right. So then I'm going to use the fact that the y. So now remember the index now is constant, no longer a variable. So we can invoke the fact that the y and the Poisson process are independent. So I can split. Basically, I can split probability yn plus k being y, yn being x, and then I have probability of nt plus s minus ns being k. I guess I can go one step further because I know the independence increment, so ns being that. This is because y and then nt plus s minus ns and ns are independent. Yeah, because they are independent. So I can split. Okay, so now once I have the y by themselves, I can just invoke the Markov property on the y. So, okay. What is that? The probability concerning the y. What do I have to do here in order to get the transition matrix of the y?
Write them into
Conditional probability. So that right here is simply P of how many steps? K step. X jump into y. Probability of y n is equal to x. Yeah. Because, well, I guess probability of y n plus k in y n in x. This is probability of y n plus k in y division on y n in x and multiply by y n in x. Right? And okay, so now, well, I just have to rewrite the other two probabilities. I have nt plus s minus ns u k and probability of ns u. Okay. So now, one step further. This is, well, it's a Poisson process. Okay, here we write pk, x jump into y, and u x. This is e minus lambda t to the k factorial. Then I have probability of ns u. Right? Okay. So then we're gonna group now. Okay, group. So I have, so remember this is the index of n, this is the index of k. Alright. So now they are, so think about the two indices now are independent. So I can just say sum of k. If I sum of k, I have pk xy e minus lambda t to the k factorial, and then I multiply with the summation of the little m probability y n dx probability ns u. Yeah. See that? Because you think about, like, so k and m now, they become independent. So if I sum of k, suppose I keep the m sum of k, then basically this is a common term, this is a common term to be pulled out. So that's why I can sum of the k without any difficulty, without any dependence on the n. And similarly for the summation on the n. Alright. Okay, so now so now I'm going to invoke facts that are independent. I bring the ns with the yn together. Alright, so this is probability yn b and x and ns b and n. Then because they're independent, and one step further, one step further, so I can keep the summation on k, whatever on k. Now the summation on n is, that will be just like probability of y sub ns being a little x. Alright, sorry, so ns b and n. And this summation now is simply again, now the probability of y and s, e and x, which is the same as probability of x sub s, 0 x. Alright? this is simply here just the law of total probability. So this is law of total probability, right? Just combine. So remember, so from the beginning, I split everything using the law of total probability. At the end of the day, I combine everything back using the law of probability. Okay? And then this, that is just the definition of the process X. Yes. Anyway, so what I have done so far is the following. I have established that this intersection is equal to, all right, so that intersection xt plus sby times sp of x is the summation on the k. What is that? Pk plus y e minus lambda t to the k over k factorial. This summation multiplied with probability xs is equal to x. That's what I have established. Alright, and so now we're going back to this, right? This intersection is that product of the series and the probability of x, sp, and x. So, and that will be cancelled out the denominator, and the answer will be summation pk xy. I guess I have the e minus lambda t staying outside. And then I have the lambda t to the k over the k factorial. Because the denominator is gone. This denominator is cancelled with this term. So as you can see now, this only depends on what I have the difference in time, which is t, the x location, and the y location. Right? Which, well, apparently this is complicated here. We cannot simplify this. We cannot simplify this series because p to the k, that is the k power of the transition matrix for the y. So we cannot really simplify it. It's not like the power of the phy. No, it's not. Anyway, so that's another example for a continuous time Markov chain. We also have some other examples in the textbook, but I guess I will discuss that next Friday through some exercises. Now let me finish this section by the theorem on the Chapman-Kolmogorov equation. So I have p of t plus s times y is just the summation on the little z in the state space. That will be either way to go with it. So p, suppose I start at s, x jumping to z, and then at z jumping to little y in this time. Okay. This is pretty similar to the Kolmogorov equation for discrete case. In other words, you can think about the matrix pt plus s. It's just a product of what do I want to go? I want to go ps times pt, which is also equal to pt times ps. In other words, if you have a condition matrix, then they are what do I call this? This is commutative. So What's wrong with the oh shoot. Anyway, so the proof is pretty straightforward. So let me just refer to the textbook or lecture note. Then we move on to the chapter. Sorry, the section. The next section, section 2, the transition rate. Okay. Keep track of the time. So what is the idea of the transition rate matrix? So recall from recall in the discrete Markov chain, right? So the n step transition matrix is basically the n power of the one step transition matrix. This is what we call it. This is the n power of p, and that is discrete time. And it's very tempting to think, okay, for the continuous time, we may have a similarly property, but the truth is no, it's not. So however, let's say however, for continuous time Markov chain, there exists an analogous equation of the form like say p sub t of xy is p, let's say p sub 1 raised to the power of t as 1. Okay. We don't have such a equation because we don't have the notion of a non-integer power of the matrix. We don't have such a notion. You need to take like you gotta go to grad school in order to know that. Here we don't have this thing here. So this does not make any sense. Okay. And so how do I determine, like, let's say, how do I determine the future matrices? How do I determine that? For the discrete case, it's pretty straightforward. If I know one step, I can determine any step in the future. But now, how about the continuous time? So the observation is, suppose the matrix PT is known for all t up to a time, let's say t naught. Suppose I know that. Then by the Chapman-Kolmogorov, then actually we compute, then PT can be computed for all t greater than t, right? So if I know the matrices for all t up to a time t naught, then I will be able to compute every t. So the idea coming from the Chapman-Kolmogorov equation, so you do inductively. So 0 here, t naught, 2 T naught, 3 T naught as the following. You see this? You see this? Suppose you have a T here. Alright? So I know everything up to the time T naught. I know everything here in this interval. But how do I compute the matrices in this interval? So what I do is just a geometrical approach. Let's say for the T belongs to the what? T naught up to T naught. Okay. So the geometrical approach says Pt is equal to this length multiplied with this length. So that will be Pt minus T naught times I guess to keep the flow. So I know up to T naught and then Pt minus T naught. Alright? That is geometrical equation basically. And similarly, so now you do inductively. So you cover every matrices in this interval, and then you inductively you can cover everything in this interval, basically. So inductively. So the idea coming from the fact that I know everything up to a time T naught, and if I have a really tiny T naught, I can talk about the derivative. Alright? If I take T naught down to 0, I can talk about the derivative if I can. Or suppose the derivative exists. So that's why they have the following. Okay, so let me finish this. And inductively, for all T inside of and T naught, and this one T naught, I have T is E and T naught multiplied with T minus N. Alright, so definition for the transition rate matrix. What do I have here? Suppose the following limit exists. Suppose I have Pt minus I, the identity matrix, divided by T, limit as T going to 0. This, well, of course, this is a matrix. So I have a matrix subtracting another matrix. So this limit exists entry-wise. Alright. Suppose that limit exists entry-wise. That means every entry. Okay. So that means every entry here taking the limit, then it exists. Entry-wise, then. Okay, so maybe we call Q here to be this. Then Q is called the transition rate. Transition rate matrix. Right. Remember, the identity matrix is just the P naught here. Remember that. Yes.
Why P naught is the identity matrix?
Remember that.
It's just by the definition.
Well, I was
particular reason for that.
I would say that is pretty intuitive. Think about, suppose I am at the time T, I am at the location X. Then when we move to the next 0 at the time, P naught, say X. Think about X, T here, X. This is 1. And obviously, suppose if I have a P naught of some X and Y, that has to be 0. X, T, B and Y, given X, T, given X. identity matrix. Okay. So you can think about, that is just the derivative evaluated at the time 0. Set t down to 0. I have to the function subtracting at t subtracting x0 divided by t. That is the derivative, basically. Derivative of the pt. Okay. And moreover, so I guess let me mention that, okay, by notation, q is denoted by q little qxy. Right here, the little qxy is called jump rate from x to y. Okay. I'll come back to the jump rate in a moment. But for now, just think about as a definition. I will explain the jump rate in a moment. Okay. So what is the I guess the lemma that I need to mention here is the following problem. Suppose if I have what do I suppose? Suppose my state space S is finite. Alright. And suppose the limit exists. Suppose S is finite and Q exists. Okay. Suppose, alright, then what do I have? I have well, I guess I don't even need I don't need that for the moment. So I just need, okay, suppose Q exists first. Q exists, and then 1. I have Q of x is always negative, and Q of xy is always non-negative for all x. The second part, what is about, suppose if S is finite, and this is always guaranteed, Qxx is equal to the negative, the sum, Qxy. This is for y not equal to. Why is that? Well, basically coming from the fact that we assume the limit makes sense. You see this? So what is Qxx? Well, Qxx is the limit as t going to 0 of pt xx minus the identity evaluated at that spot is 1 over t. Right? Because identity matrix, Ixx, which is P naught xx, is equal to 1. And now, of course, PT is just a probability number. It's supposed to be less than 1. So the denominator is a negative number. So the limit has to be non-positive. So this is always less than 0, right? So that is for the Qxx. Similarly, for the Qxy. Now, if x is not equal to y, this is the limit t going to 0, pt xy, but now that is just 0. Here the difference, subtracting away 0, and that has supposed to be non-negative because identity matrix evaluated that at this entry is 0. Okay. So how about this relation? That comes from the law of probability, because you realize at the time t from x, they got to jump to somewhere. So, well, I guess that. That is f1 and f2. Suppose x is finite. What do I have? So I have qxx is the limit of what is that? The limit of pt x minus 1 over t. But however, the number 1 there, right? Number 1 is not number 1. So limit of ptxx minus the summation on the z ptxc. Alright, divided by t. Now, law of probability. At the time t, I have to jump to some z, whatever they could be. And so if I get rid of where the z being the little x, so that is the limit of the negative sum pt x y, where y is not equal to x. Alright? Divided by t. And remember, because here I have my state space S being finite, and so limit of the sum is the sum of the limit, because the sum is finite. So that would be minus sum y must equal to x limit ptxy over t going to 0, because this is a finite sum. A finite sum. So that's why you can do it. Alright? It is not a finite sum. In other words, suppose it's like an infinite sum, then you gotta be careful. You have to be careful. You need to impose further regularity condition. But here we have a finite sum, so nothing really identical. Anyway, so that is going there to because x is not equal to y, that is minus summation on q x1. Y not equal to x. Right? So in other words, suppose if you have a transition rate matrix, sum of each row is identically 0. The sum of each row, think about like you have a say suppose you have q here. Alright. Think about x here, y1, y2. So x is here. Right, so the negative qxx. We have qx y1, qx y2, and qx yn. So as you can see from this relation, if I take a sum of the row, then the sum is supposed to be 0.